Rate law. What is rate law? Rate law is the rate of reaction that is proportional to the concentration of your particular reactants. Okay, so these will be your reactants. Okay, they could also be catalysts too. They're just not consumed in the reaction. Okay, so we have a rate of reaction. Well, we can actually make this simplified. So we just have rate is equal to our K. Okay, our K here is going to be our slope. I'll explain why. Okay, but this is going to be our K, and it's going to be the same thing. It's going to be multiplied by our concentration of reactants. Now, what is this K? Like I said, this is our slope. Okay, sometimes we call this the proportional constant. Okay, now why is this the case? Well, let's draw out a little graph over here, and let's say it has this kind of pattern. Okay, and obviously here is going to be a little time zero. Okay, so time zero here. You know what, I'm just going to put time here. Obviously it goes from left to right, and then we're just going to use a concentration time curve, okay, which is the standard. So we just want the concentration, it increases from down here and it increases going upwards. Now at time is equal to 0, so right over here, time is equal to 0, this is, at time is equal to 0, this is the best place to be looking for the particular slope. Why? Because no products have formed. Okay, at time 0, all the reactants are still about to hit that activation energy barrier complex at the activated complex, and then if it proceeds and progresses, then products start being formed, and then it can be a little bit more tricky to gauge the calculation, right? But if there's no products formed yet, this is perfect. It's easy to signify. So at time is equal to 0, our slope, our best way to represent it is our y over x. Okay, why is this the case? Well, y is the y-axis, concentration is over there, hence why our concentration is going to be over time, or y over x. So here, another way to say this is our change in concentration, okay, over our time. Okay, so our time is going to be on the denominator. We'll just put our change in time. It's going to look like that. Again, so since no products were formed, okay, so since no products formed, at this time, it is the best measure. Okay, of accuracy regarding rate. Okay, now I also want to preface it here that even though I'm saying it's regarding of rate, because our obvious topic for this video is rate law, right, finding out the rate of reaction, this here is at time is equal to 0. This means that we're not at rate, we're actually looking right now at the initial rate. So I might just put down here initial rate, okay, because time is at 0 right now. So another way to say this, I know we have our slope over here. Our slope we've calculated is going to be y over x at that particular time. Technically, y over x is initial rate as well, because that's when we took this y over x slope, right? Obviously, here is the best time to be looking at the slope. Look at a tangent over here, and y is over x at that particular point in time is very accurate. But again, this is at time is equal to 0, so it's not just rate. We've actually found our slope at our initial rate. So I'm actually going to be putting here initial rate is technically also y over x, our slope. Now, if I were to write this out again, if I wanted to just look for y and isolate it by itself, I have to multiply by my division of x, right? Because the opposite of dividing x is times x, so I'm just going to do that. That way they cancel out. If I do it on the right side, I need to do it on the left side. So technically, my y is also known as our x. And in this case, it is time multiplied by our initial rate. There we go. Okay, now we're not done just yet, because y is also going to equal, remember, x is our time, right? However, if our time continues towards the left to right direction, but we have initial rate here, which is time is equal to 0, this means that this is no longer going to be initial rate anymore, because if we multiply our time with our initial rate, again, this was at 0, but now we are actually starting to progress with time. This is no longer going to be initial rate. So technically, now our x times initial rate is actually just going to become rate. Okay, hence why we're getting closer to dignifying what our rate law represents. Okay, right now y is equal to the rate. Now we're just going to turn this into something that you're a little bit more accustomed to seeing. I know we've put our x included in the rate, but let's break it up again. Okay, x times initial rate again. But I'm going to keep my x here the way it is, but I'm just going to change my initial rate. Okay, so instead of initial rate written in this way, I'm actually going to make it as y over x. Because remember, initial rate is actually y over x. So I'm just substituting that over here visually, okay? Now, y over x, what is it? It's also known as you can see over there, the slope. So technically, we are multiplying by slope right now. So instead of y over x, which came from the initial rate, I'm actually going to change it now into the slope. So y over x is now going to become m, okay, which is our slope, and our y. Okay, so now this is going to be y is equal to mx. Okay, and I'm sure you've already learned in junior grades, y is equal to mx plus b. Okay, we're not going to use b, okay, it's just going to be 0 because as you can see over here, the line is not going through the y-axis, okay, so we can't put b. Okay, so b is just going to equal 0. We're just going to negate it. Right now, what's more important here is our y is equal to mx. Okay, now whenever we start doing our rate law, okay, or rates of reaction, then we're not going to be using m. We're actually going to make it represented as k. Okay, but they mean the same thing. So from now on, we're just going to use as y is equal to kx, okay, or y is equal to k times x. Now remember, this is no longer going to be just initial rate. Okay, we are now progressing in time. This was time, right? So this is no longer just going to be time, because as time progresses, our concentration changes. Okay, so these kind of work in conjunction with one another. Our x is not just going to be represented as time anymore, it's also going to be represented as concentration. Okay, because remember, as time goes forward, after the initial rate at t is equal to 0, after that, our concentration starts changing, right? Our reactants start becoming our products and might reverse back and forth, etc. So as soon as time progresses, our concentration changes. So we're going to dignify that over here, okay? So it's no longer just going to be x, it's going to be the concentration of x, hence why it's in brackets, okay? So technically, I'm going to write it up here again, y is equal to our kx, okay? Or our k concentration of x. That's how we're going to be approaching this rate law formula as we go throughout this video. Now I'm going to look at two different types of orders, okay? A first order graph, and we'll also look at a second order graph. Now for our first order graph, it's going to look somewhat like this. Okay, whereas our second order graph is going to look somewhat like this. So if this is going to be our first order graph, how are we going to represent it as a formula? Well, right now, obviously, we're looking for rate. Okay, we're getting closer to this rate law figure. And remember, rate, in case you forgot already, rate is equal to our y, here our initial rate times our x, okay? But this, in general, is going to be y is equal to our rate. And obviously, right now, we're trying to find, always, we're trying to look for y. We're trying to see the rate, okay? How is the rate going? This way versus this way, okay? As indicated as an illustration. So what is our rate, okay? What is our rate? Well, we got to find our y in this case. So I'm just going to put y is equal to what? Okay, y is equal to, obviously these have a slope, right? So this has a particular slope. Obviously this one is a higher slope, okay? And this one is obviously smaller, okay? So I'm just going to putting here, okay, our m, okay, is lower, okay? And here our m, our slope, is going to be higher. So again, y is equal to what on each one? Well, obviously this has a particular slope, so we'll just put our k, okay? Again, k and m are pretty much the same. And then what is going to be our concentration? Okay, let's say our concentration is x, okay? Our concentration, let's say, has a particular exponent on the top. Let's say it's m, okay? if this is going to be represented as 1, this here is a first order reaction. Okay. However, if this is represented as 2, then this is no longer a first order. This is now a second order. Okay, so it has to be represented as 1. So on this side over here, if we have our slope here and our concentration, if this here is 2, this here is a second order. Okay, so this makes sense. If this was a 3, that would be a problem. This will be a third order graph. Okay, now it doesn't always have to be listed that way. So let's have our y is equal to our k and our same x, right? But rather than having just one concentration, let's say we have 2 concentrations. Let's not use y because y is already here. Let's use z. Okay, if this has a particular exponent and this has a particular exponent, okay, I'm just doing n, okay, because n comes after m. You could use any variable you want. This could be a or b, or it doesn't matter. Okay, so our m and n are here. If this here was 1, okay, and this here was 0, this is still a first order, because remember, with our exponent rule, our exponents here must add each other. So 1 plus 0 just keeps you 1. So you still have a first order graph. However, if this is also a 1, now you have these exponents adding to each other. Now this becomes a second order. So technically this one would actually be a second order looking graph. Okay, so similarly on this side over here, if we had, okay, let's just do 2 concentrations again. You could have 3, it doesn't matter. Okay, but let's say we have, okay, m and then n, and this one here, let's say we have, I don't know, 0, okay, and this one was also a 2. Okay, this here is still a second order. This is correct, because once you add them together, you have a second order. Okay, it just gives you a sum of 2. So this is what the first and second order graphs are. Okay, a third order would just be a 3. Okay, so let's say you have m and n, okay, and o. Okay, if each of these are 1, 1, 1, you add them all up, it still gives you a third order. Now I want you to look at these particularly important formulas as we are approaching closer to the rate law. Our first one is going to be our rate number is going to equal our slope, and then we're just going to put our x's here. It's going to be exponent of m. Again, it doesn't really matter what letter you put over there. Let's put, let's say, z over here, and let's say this one is an n. Okay, you're going to divide this by another rate number, and you're going to equal that, again, divided by our slope, our same types of concentrations as such. Okay, figure out how to do this one, which we're going to be looking at a few practice problems a little bit later on, and you become succinct at it. We are now going to take what we've learned from there and apply it into our actual rate law. Okay, so this here is our rate law. We have rate, okay, is equal to our k, our slope, multiplied by our x to the m and our z to the n. Okay, so this here is what we're going to be using. So looking at this particular question over here, what is the rate of formation of y if concentration of B is doubled? Looking at our chart here, we're only given this particular formula at the very top, but there's a whole bunch of numbers here, and the only thing that we can identify in A is y. Okay, where is y? Okay, I see y over there. Okay, how about B? Okay, if B is doubled, I see that over here. But which one? Are we using B here, trial number 1, or trial number 2, or trial number 3, or trial number 4, and trial number 5? Okay, all of these trials. Which one are we going to be using? We don't know. It doesn't say. Okay, same thing for here. Which one are we going to be using for the rate of y? It doesn't say. Okay, so we can take this as a general kind of question. So we don't even need to use these kind of complex formulas. Okay, we can just look at our previous formula, our definition of rate law. Okay, what was our definition of rate law? Our definition of rate law was rate, okay, is proportional to our concentration, okay, of our reactants, okay, or rate is equal to what? Our slope multiplied by our concentration. Okay, either one works. So if you just use a simple approach, if we're looking for the rate of formation of y, if this concentration is doubled, we know that, again, this one is a doubling. Okay, so if this doubles, okay, by a times 2, this is directly proportional to our rate. So if this one doubles, what do you think is going to happen to our rate? Obviously, it's going to double as well. So that's honestly that simple. Okay, the answer for A is it doubles as well. Okay. okay, based on what was shown over here in the beginning of our video. Okay, now let's look at B. What is the rate of formation of Z in trial 3? Okay, so now we're getting a little bit more specific. So we have trial 3 over here, rate of formation of Z. Okay, we don't have Z over here. This is a big problem now. Okay, so what are we going to do? We're going to take this, okay, that's in the question, and there is a Z over there. So this is our little hint, okay, so let's get there. So our A plus our 2B plus our 3C gives us our 2Y plus our Z. Okay, I have my Z over here. I need to find, obviously, this one. So what is the rate of formation of Z in trial 3? Okay, so again, we're in trial 3 right now. What are we going to do? Well, formation of Z is not really able to be found because in our chart, we only have rate of Y, or concentration of Y, okay? By the way, this big M here, okay, our M is standing for moles per liter, okay, per second. Sometimes it's written this way, in case you're probably confused as to why, okay, just look at my previous video, okay, link is in the description for the rates of reaction, okay, explains this in detail. Now, we're trying to find our Z, okay? Again, we can't find it. We can only find our Y because that's the only one that's given to us, okay? So we'll eventually find Y, and then we can eventually find our Z after. Okay, let's take it in steps. So what is the rate of formation of Z in trial 3? Again, we're focused specifically on trial number 3 right now because that's what the question is given us, unlike the previous question. Okay, now it's a little bit more specific. We're looking only at trial 3. Are we going to be using our initial A, or are we going to be using our initial B, or are we going to be using our initial C concentration? Well, it doesn't really say. All it's saying is trial 3, okay, and then just find the formation of Z, okay, so it doesn't really matter. That means I'm just going to use any, okay? I can use B or C or A, okay? I'm just going to use B for now, okay? So where is B? Okay, I have 0.02 over here, okay? So I'm just going to look for my 2B, okay, which is my 0.02, but for now I'm just going to use a general 2B. I can put the 0.02 a little bit later. So this 2B here, again, I'm going to multiply it by a molar ratio. Why? Because I'm trying to find my Z, okay? But I'm not going to get to my Z just yet. I want to go to my 2Y first, okay? Why is that the case? Because at least my 2Y has some values here, okay? Once I get those particular values, okay, then I'll be able to get that and then turn it into my Z, okay? I don't have my rate of concentration, okay, of Z over here, so why would I do that? Okay, I'm just going to use what I have or what I can get first. So I'm going to put my 2B, and they're going to be multiplying, okay, diagonally over here. That way they can cancel out, okay? So if my 2B's are going to be canceling out, what do I eventually want to get? I want my 2Y, okay? So eventually this cancels out, I end up getting my 2Y, okay? So it's pretty much the same, obviously, because the coefficients are obviously the same, okay? 2 versus a 2, so obviously this should be no surprise. So now I have my 2Y, okay? So I have my 2Y right now. But I need to now go from my 2Y to my Z, okay? So I'm just going to multiply again, do my molar ratio so that my Y's cancel out. Again, we're not trying to look for my Y's. I'm trying to look for my Z's as indicated in the question. We're trying to look for Z, okay? So I want to get rid of my Y's, okay? How many Z's are there? Okay, there's only one Z, okay? So that way we have to multiply by 1 over 2, okay? If we multiply by 1 over 2, this is 0.5. And again, what is my 2Y value? Okay, so let's just go backwards a bit. Instead of 2Y, I could actually change my 2Y into our actual value. Okay, what is my value of 2Y? Where is it? Right over here. Okay, yeah, trial number 3, it is 80. Okay, it's 80 moles per liter per second. Again, we're going to put our 80 moles, okay, per liter per second. Okay, this here is our 2Y. Okay, and again, this here is my 2Y here on the bottom. Okay, which is pretty much this, right? This here is my 2Y, so technically they're the same, okay? And my 1Z is going to be on the top over here, okay? So what happens? Well, obviously, my 80 here needs to multiply by my 1, but I also need to divide by 2, which is the same as times 0.5, or just divide by 2, okay? So that means instead of my 80, what do I end up getting? I end up just getting 40. Next, C. What is the rate of disappearance of C in trial number 2? Now this is where it gets interesting. Rate of disappearance of C means that even though it's disappearing, it doesn't just go away and vanishes in thin air. It's not magic. It's eventually going to be formed, right? If it disappears in the reactant, it's got to form somewhere, okay? So instead of disappear, we can actually highlight this as forming as well. Okay, if it disappears, it's got to form. So we have our equation over here. And again, C is going to be disappearing, so I'm going to be looking at this one over here, okay? But I'm going to be using this as an end point, okay? Because remember, whenever I have my 3C, this means that I'm taking out 3 from the jar, let's say in this big jar over here, I'm taking out 3 for every 1 mole of A, or for every 2 moles of B. So if I were to look at it this way, all in a jar, for every 1 of this, I take 2 of this and I take 3 of this. Which one is going to be running out first in the jar? Which one's going to be limiting? Obviously this one, okay? So I want to relate this disappearance in comparison with something like this, or in comparison with something like that, okay? Now, if this is disappearing, it is also going to eventually form on the other side, okay, on the product side. Now, I'm trying to use disappearance of C in trial 2, so I'll have a look here, trial number 2, okay? And where is C? That's right over there, okay? It's 0.04, and what is it going to create? It's going to create our Y, okay, our 15 moles per liter per second, okay? So if this is my 2Y over here, I'm going to write this down, okay? I need to multiply it by a molar ratio of 2Y down here, that way that they can cancel out, so that I can eventually, find my 3C, okay? Because remember, my 3C is disappearing, okay, but it also needs to form, okay? Because it's going to form into and become a product. So I'm going to put my 3C here on top, okay? So if you look at the molar ratio over here, okay, because technically I know I'm canceling out this one, but technically our 2Y here is what? It's our 15 moles per liter per second, okay? So I can just kind of, instead of putting our 2Y over here, this is technically 15 moles, okay? Yeah, I'm just running out of space here. 15 moles, okay, per liter per second, okay? Now, if that's the case, this is my 2Y, and this here is my 3C, and it's all over 2Y. Technically, my 2Y here isn't canceled out yet. It's just over here, okay, because this here is 2Y as well. So I just do this value multiplied by my 3 over 2, which is going to be 1.5. Okay, so I just do 15 times 1.5. What do I end up getting? I get 22.5. Okay, so that's my answer, 22.5 moles per liter per second. That is the rate of disappearance of C in trial number 2. All right, let's have a look at D over here. What is the rate law derived for the above data? Okay, rate law is obviously this one. This is our final step that we're trying to get to, but we cannot get here unless we start doing this. Okay, so again, this is a rate law. We got to do this first before we end up doing that. So we're going to get our first rate number divided by another rate number, but which one are we going to be used, right? This rate or this rate or this rate or this rate? We're trying to eventually find our missing compartment, okay, our missing concentrations and our missing exponents over here. So how do we know what numbers there are? Are they like 0? Are they 1? Are they 2? Are they 3? Okay, so that we can figure out if this is a first, second, or third order rate of reaction. Okay, well, what is the rate law? We're gonna use a particular one where we have the same ones. So these here are the same, and these here are the same, but these here are different, okay? We want to find those kind of examples where we have everything the same, okay, in terms of our concentrations, but the only thing that's an outlier that's still missing, that is not the same, okay, it has to be left over. So this is perfect, okay, because these are the same, these are the same, okay? Obviously just this one is not, okay? So this is what we're trying to find. So this is perfect, okay? So let's use trial number 1 and let's use trial number 2. So let's have our rate, okay? It's going to be 15 moles per liter per second, okay? All over our second rate, okay? Which is going to be this one over here, our 10 moles per liter per second. Perfect, okay? Now I'm gonna equal this into our slopes. Okay, what is our slopes going to be? Well, we have no idea. Okay, it's not written here at all, so we have to just put our k here and just leave it the way it is. And then again, this is still all being divided together. So what is our first concentrations? Okay, so our first concentration, okay, is going to be our x's. It doesn't matter. I know we have a's here, so we could just make our x here the same as this a, this z here is the same as this b, and then this c here could be like another one that we can just make up. So let's have our a's. So this is going to be 0.10, and this one here is also going to be 0.10. Perfect, there we go. Okay, and in terms of its exponent, it's just going to stay like that because we don't know what the exponents are, so we'll just leave it the way it is. Next, we have to multiply it by our next one, okay, our z's, okay, so also known as our b's, okay. So we have 0.03. Okay, same thing here, 0.03. Okay, and obviously we have to have our exponent, and our exponent over here, this is going to be our n, and this is going to be our n. Okay, so right now everything's kind of falling suit, okay, towards each other. Oh, sorry, instead of 0.03, I meant to say 0.02 over here. 0.02, okay. Okay, so everything's falling suit, and then this one here is now going to be the same, so let's also multiply it by here. This is our c, okay, so we can put 0.04, and again 0.04, and okay, we can just do O, okay, MNO. So what are we going to do? Obviously, we just divide them all together. So obviously, these will divide, okay? Obviously, our 15 divided by 10 will divide, but it's going to be something left over. So 15 divided by 10 is 1.5, obviously. So we have 1.5 here. These cancels out perfectly. Okay, we'll just do that. And then our K's cancel out perfectly, so that goes away. These cancels out perfectly. This and this cancels out perfectly. These and these cancel out perfectly, these and these cancel out perfectly, okay? So what you end up just getting is our 0.03 divided by our 0.02. So what we're going to do, we'll get our 1.5 is equal to our 0.03 divided by our 0.02. Just try it on your calculator. I'm just getting 1.5. Okay? And of course, this has to be to the power of n. Okay, how do we know what it's going to be? Well, obviously, 1.5 to the power of 1, okay, is going to give you our 1.5. So therefore, n is going to be equal 1. Okay, so our n value is 1. Alright, now we're going to do the same thing, okay? But instead of using our trials 1 and 2's here, okay? We've already found n, now we got to be finding the other two, okay? M or O, okay? So let's have a look at other ones that are the same. Which ones are the same over here? So obviously this one here and this one here. Oh no, but this one has a question mark, so let's not use that one. We could use, okay, this one here and this one here would be perfect, okay? So that way we can find our O, okay? So we have this one and this one are the same, okay? So perfect, let's try that one. So we have trials 4 and 3. Okay, let's give that a try. So we're going to put our rate, okay, 4 is going to be on the top, so we'll have 160 moles per liter per second, okay, divided by our 80 moles per liter per second, and this is going to equal our slope over here. Nothing changes. Okay, our first concentration, what is it going to be for trial 4? Okay, it's going to be 0.20. Okay, so 0.20. This is also going to be 0.20. They're the same, and obviously it's going to be our M's, okay, or our A's. Okay, doesn't matter. And then we have our B's or your N's, however you want to say it. Okay, it's 0.02. Okay, so 0.02 here, and this one's also 0.02 over here, and these are going to be our N's. And then the last one is going to be the different ones. Okay, so 0.16 is going to be our O's, and this one here is going to be our 0.08. There we go. Okay, so now we're just going to start dividing. Okay, sorry, I forgot to this. We're going to start dividing now. Okay, so obviously 160 divided by 80, what do you end up getting? Obviously 2. These cancel out perfectly. These cancel out perfectly. These cancel out perfectly. And these cancel out perfectly. But just these don't. Okay, so you get just a 0.16 divided by a 0.08. Obviously that gives us a 2 as well. Okay, so obviously 2 to the power of 1 is going to be giving you 2. So obviously 0 Okay, so our O is going to equal 1. Okay, so our O is also 1 as well. Because now that we're done that, we now eventually have to find our M. Okay, so we still haven't found that yet. Well, remember, our order is M, N, O, right? M, N, and then O. Okay, so this is obviously our M, this is our N, and this is our O. We've obviously found our N, we found our O, but we did not find our M. Okay, well, that means our N's have to be the same, our O's have to be the same so that we can find our M. Can this work out? Well, these are the same, but these are not the same. Okay, these are the same, but these are not the same. Uh-oh. So how do we eventually end up finding our M? Okay, it worked out great for these ones, but it's not working out so great for the M. At this point, you can honestly just carry on and continue. It doesn't really matter because we actually have 2 out of the 3. So in mathematics, if you have 2 out of 3, that last one is going to eventually be found. Okay, so we're actually okay. Let's just continue and do this. So let's say, I don't know, we use, let's say 4 over here, and let's say, 2. Okay, doesn't matter. Let's give it a try. So we can have our trial of 4 and our trial of 2. So let's have our 160 moles per liter per second, okay, is equal to, what is it, 0.20. 0.20. Okay, this is going to be our M. And then what else do we have? We have our 0.02. This is going to be our N. And then we have our 0.16. And this is going to be our 0. Okay, so our O. And then just start dividing, okay? So let's use 15 over here. And then this is going to be our slope. We have our 0.10. What do we have next after that? We have our 0.03. What do we have after that? We have our 0.04. There we go. So let's just continue to do what we need to do. Okay, so obviously our M's are M's. Okay, we can obviously keep it the way they are because we don't know what it is, but for our N's and our O's, we can actually put the particular exponents that we found in the previous work to eventually figure out our M's to be isolated. Okay, so let's first do our 160 divided by 15. Just use your calculator quickly. You end up getting 10.66. Let's say 10.66. Okay, this obviously cancels out really, really well. This cancels out really, really well. Okay, and what else? We got our 0.20 divided by our 0.10. That's obviously a 2, so we got a 2. Okay, let's keep that over there. And then these, 0.02. Again, this needs to change into a 1, right? So let's actually just change this into a 1. And this one here as well, change this into a 1. And our O here, again, change it into a 1 as indicated here. And this one too, change it into a 1. Okay, so we just get our 0.02, technically just divided by our 0.03. What do you end up getting? You get 0.666666. Okay, and then you just do this over here. 0.16 divided by 0.04, you end up just getting times 4. Okay, that's it. So let's figure out the rest of this work. So just do our 0.666 times 4. What do you end up getting? I end up getting 2.6664. Okay, times our 2 to the M, and this is our 10.66. Okay, so just divide this side by 2.6664, divide this side by 2.6664. Obviously these cancels out, so I end up getting 2 to the M is equal to whatever this is. So try it on your calculator. End up getting 3.99, so that's technically a 4. Just round it up. Okay, so 2 to the power of what gives you 4, obviously a 2. Okay, so that for M is equal to 2. So we just put our 2 over there. So now we've pretty much finished it off. How do we end off this question? Okay, for D, what is the rate law derived? Okay, we have to make it look like this. Remember, this is the formula for the rate law. So therefore, our rate is equal to our K. We don't know what that is, but it's fine. Our X, okay, is going to be to the power of M, 2, okay, and then it's going to be our Z, which is going to be to the power of, what is it, Mn, right, so 1 over there. Okay, perfect. And then we don't have a name for the third one. Okay, we'll just put W. Okay, and it's going to be also a 1, Mno. Okay, so Mno. So that there is a rate law. Rate is equal to the slope times the concentration of x to the 2 times the concentration of z to the 1 times the concentration of w to the 1. That's the answer. If this is kind of confusing to you because we've just been using like A's and B's and C's, okay, you can do it that way too. It really doesn't matter. So if you want, we could do rate is equal to our K is equal to our A. Again, this is to the 2. This is our Z. Sorry, our B to the 1. And this is our C to the 1 as well. All right, let's look at E now. Okay, what is the missing rate? Okay, well, we have to find our rate over here for trial number 5. Okay, it's not given to us. Well, we obviously know that this is the formula we're supposed to be using, our rate. Okay, but if I were to key these in, okay, because we obviously know a lot about our exponents here and a lot about our concentrations, but we don't know what our slope is. Okay, and obviously we need all of these values. Okay, none of them can be unknown. We need all of them. We do our calculations on a calculator, and then we'll eventually find our rate. But we don't have our K, so this is a problem. So we can't just punch it all in right now. We have to eventually find our K. So how do we find our slope? Well, I'm just going to delete this over here. In order to do that, we have enough values here just to use some other random trial here, okay, and then we can eventually find our K because we have so many values. Okay, we have so many trial values here for our concentration. We have all of our exponents, so we can obviously eventually find our K. Okay, because we have our rates as well, so it really doesn't matter which one we use. Okay, let's use number 4 for example. Okay, so again we have our rate. Okay, so our rate is going to be 160 moles per liter, okay, per second, is going to be equal to what? Our K. We have no idea what it is, but we know for our trial 4 we can use 0.20. Okay, and it's going to be to the power of what? We know that this is going to be m and o, right? So this is the first one, so we're going to be putting a 2 on the top over there, and then we are going to multiply it by what? We have next, we have again 0.02. Sorry, yeah, 0.02. The other one was 0.20, so this one's 0.02. Okay, and again, this is for our n, so that would be 1 over there. So let's write that up there. And then last one, we have 0.16. Okay, and 0.1, that's going to be our O. Our O is going to be our 1. There we go. Okay, so we've pretty much done it. And we can obviously isolate for our K. Okay, so let's give this a shot. And remember, all of these values here, okay, is in moles per liter. Okay, they're all in moles per liter. So there we have it. Okay, so we can just start adding all of these together. So we have our 160 mole per liter per second is equal to our K, and then let's just do the product of all of these. Just to put it into a calculator, and end up getting 1.28 times 10 to the power of -4. Okay, so obviously I need to do a division on this side so that they can cancel out. So if I do it on the right side, I need to do it on the left side. So I have my K just ends up just getting this being divided by that. I end up getting 1,250,000. Okay, this is going to be my K value. So now we have our K, so this is our missing piece of the puzzle that has been solved. So now we can just do our K, okay? So rate is equal to, we're just following this formula here, K, which is 1,250,000, okay? And we have to multiply it by our X, okay? What is our X? It's going to be right over here, 0.05, okay? It's to the power of what? Our M, okay, which is going to be 2 over here. Multiply it by our 0.01, and that's going to be to the power of 1 over here, our n, and then last one we have 0.08, and that's going to be to the power of what? O, which is going to be a 1. There we have it. So you're just going to plug this all in together. What do you end up getting? End up getting a value of 2.5. All right, lastly for F, what is the rate constant? Okay, obviously rate constant is another word of saying the proportionality constant or proportional constant. And remember, at the beginning of the video, I did say the proportional constant is also known as a slope, also known as K when we deal with the rates of reaction, okay, and the rate law. So isn't that this one over there? That's the answer. K is equal to 1,250,000. That's it. We're going to continue to do more practice questions in the next video for more help for your comprehension.